Good afternoon. I'm Gord Cook, Building Knowledge Canada. Welcome to the Critical Canadian Building Science webinar series, hosted really nicely or sponsored by Enbridge. I always really appreciate that. This particular one's on large building air tightness testing. Got some really cool speakers for you. Folks been out in the field doing some cool stuff, partly from our team, partly from Nerva. We'll give people a few minutes to get on. We're expecting over 300 people have signed up, which we really appreciate. But we'll just give people a couple of minutes. We got a lot to do, so we'll go fairly quickly, but we'll get started shortly. Talk amongst yourselves. Stacy and Emma have already posted in the chat. Just if you're having troubles or link problems and so on, let us know. But we'll ask you to have your microphone on mute, cameras off, I think, for the time being. When we get to the Q&A near the end, we can open things back up again. We're doing a couple of polls to see where people are from and what segment of the industry you're in. But for the time being, we're just waiting for a few more to join. Just wait one more minute, I think.
I think you're good to go, Gord.
Good to go?
Yeah,
Great.
I think we've got that number starting like that. It just means that people are grabbing their lunches and going to head in the next 5 minutes.
Sure. Great. So again, good afternoon. Welcome to the Critical Canadian Building Science webinar series. We've partnered with Enbridge, Distribution Enbridge Gas on this. We're so appreciative of that. My name's Gord Cook with Building Knowledge Canada. We'll do a little more introductions later, but this particular segment, large building air tightness testing, lessons learned in a swiftly growing industry. And Mike, specifically, you're going to talk to people about how busy it's gotten very nicely. It's good to see. We're from 1 to 2:30. We're going to leave about 15 minutes for questions at the end, but let's get started. And I'll give you just a little bit of the agenda then, do a few minutes of introductions. Then we have a really exciting, actually, we'll have Enbridge tell us a little bit their safety message, which we always like, but then there's a really interesting offering that they have associated with large building air tightness testing. So we'll do that. We'll do just a couple of minutes on defining the value of air tightness testing in large buildings. Most of you will know that from a building science perspective. We just want to highlight a couple of things. We'll cover a little bit of air barriers and air tightness requirements and codes and standards, and then look at some of the performance criteria for air tightness and air sealing. Then we'll switch to types of air tightness testing. That'll be Kyle. Kyle will talk about standards and types of air tightness. And then we'll talk about the process of testing. That'll be Mike and lessons learned in the field. And then we have Josh from Nerva. It's going to help us with some examples of projects in both air sealing and in test results, and look at some future opportunities as well. So that's where we're headed. And I'm always pleased to introduce Susan Cudahy from Enbridge. She's the supervisor of strategic builder relationships in residential new construction. Susan, welcome. And again, as always, thank you for sponsoring these sessions.
No, thanks, Gord. And thanks everyone for attending today. We'd like to start off our presentation with our traditional acknowledgement. By acknowledging that the land on which we gather is the traditional and the historical lands of the original people of Turtle Island, who have been the caretakers of these lands since time immemorial. Today, this gathering place is home to many First Nation, Métis, and Inuit peoples, and our acknowledgement of this reminds us that our great standard of living is directly related to the resources of and relationship to Indigenous people, and that we have a responsibility to honor that.
And
So we'll
thank you.
just take,
It's kind of interesting though, Susan, just a quick second. When you think about who all joins, we often have people from across Canada and even the United States. So that literally could be certainly dozens and maybe even hundreds of First Nations groups. Very cool. So thank you for that acknowledgement.
no problem. And just a quick message that we'd like to remind people of. You as the builders, developers, and HVACs are a critical audience for us. So we do have a specifically designed builder and HVAC attachment center. So if you are having problems specifically on new gas services, using the Get Connected online attachment tool, have any questions on anything related to your new projects, subdivisions, etc., please call the 1-866-772-1045. It is a center specifically to assist your industry. If you have any questions on something that has already been done in the past, billing, damaged meters, etc., please call our customer care center. But just a quick reminder that there is a specific attachment center for you where you can get the help you need. So with that, I'm going to turn it back over to Gord, who is going to introduce Chris Chetley, who works with us.
And thanks again, Susan. And Chris, thanks for joining us. You had said to us, it's a larger building. We'd like to talk about a new offering that we have. Chris is the program advisor for commercial stream of savings by design and the commercial air tightness testing program. Chris, welcome and highlight for us this financial incentive.
Yeah, great. Thanks, Gord. Appreciate being here. Yeah, given the subject matter being discussed in the webinar today, it seemed like a good opportunity to generate some more awareness amongst the group regarding our program for air tightness, which we had launched at the beginning of this year. The program is part of our energy conservation new construction portfolio of programs called the Enbridge Gas Commercial Air Tightness Testing Program, where builders and developers can earn incentives that would reward them for developing high-performance building envelope. As we're going to learn today, air tightness testing provides the opportunity to identify and address issues before the building is occupied and avoids difficult and costly corrections after completion. The program essentially offers financial incentives of up to $45,000 for testing to resolve any issues discovered in the process. There are two streams to the offer. The initial stream, which is the air tightness testing incentive, which we offer up to 50 cents a square foot, up to 80% of the cost of the testing to a maximum of $30,000 per project. Incentives would be paid upon submission of the final air tightness testing report. And then we have an implementation incentive of up to 50% of implementation costs. The implementation costs could be a number of different things identified through the air tightness testing report. For example, aero barrier, caulking, sealing, and other envelope improvements, up to a maximum of $15,000 per project. To quickly just go over what projects are eligible, this is intended for commercial, industrial, or multi-residential new construction projects before the envelope is developed or constructed. To a minimum of 25,000 square foot or larger is the baseline. And of course, they have to be located in the Enbridge gas service area. So for anyone interested or looking for more information into this program, please reach out to Alex Colvin, our Senior Solutions Advisor, or you can reach us at uniongas.com air tightness for more information.
This is really exciting, Chris. Thank you. I was involved in some of the early conversations, and I know the directive was to help build the capacity of the industry, and this definitely is very worthwhile. So thank you for that. I'll remind you that you will get a copy. Everybody, participants will get a copy of this presentation, so you'll have this contact information. But you've got Alex would help with that. So thanks again, Chris. Very powerful. Appreciate it.
Thank you.
All right, so let's get started. Most of you know me. I won't spend too much time on my introduction, just Building Knowledge Canada, professional engineer, been working in the industry. It says 25. I got enough gray hair. It's more like 35 now, so we'll change that perhaps. But just pleased to be here and facilitating, just doing a little bit of the presentation. Also have with us Mike Gilson, who's with Building Knowledge. Mike has spent, well, it says 10 years prior work experience, but Mike, you kind of grew up in this industry. Your dad was a builder, but been doing this, taking on the large building air tightness testing here at Building Knowledge. Just say good afternoon, Mike. We'll hear from you later, but say good afternoon, please.
Yeah, thanks, Gord. Happy to be here.
Thank you. And so he manages the field and technical services division for us. And then also with Building Knowledge, senior project manager is Kyle Anders. Kyle, just say good afternoon.
Good afternoon, everybody.
And Kyle's the one who's, I would say, writing the reports. He's out in the field as well, but managing the reports and so on, and has some really good information to share on things he's been seeing with respect to standards, what we can expect, and so on. And then lastly, very pleased to introduce Josh Lewis, VP of Energy Engineering at the Nerva Energy Group. Nerva has spent years doing controls work, energy efficiency work, more recently air sealing of ductwork, and then most recently air sealing of commercial buildings using the aero barrier technology. We'll hear from Josh on a couple of specific projects that I think you're going to find pretty interesting. Josh, please say hello.
Good afternoon, everyone.
Thanks for joining us. So you'll hear from all three of those folks after I get a little chance to give you a little primer on some of these issues. Stacy, did you want to quickly do the housekeeping?
Yes, please. Thank you. Just a reminder, we do have this presentation always available. We post it up on our website once we have all the presentation information tweaked. If we made any changes today, that's why you don't get it immediately after the presentation. And the Q&A, if everyone can see that it's down at the bottom there beside the chat button there, which is why I think we get some confusion where some people put their questions in the chat field instead of in the Q&A, but we encourage you to put it there so it records it. We can answer it a little better that way. And please be respectful. Everyone here is volunteering their time and their expertise, so please be respectful in the chat. And the closed captioning is down there. If people want to see the transcript as everyone's talking, it'll show up while everyone is speaking, and you can download that chat afterwards as well. And if we can get you to fill out those survey monkeys after the presentation, we always appreciate that. That just helps us continue to deliver wonderful content to all of you. Thank you.
Great, thanks, Stacy. And then we always like to write a couple of polls just to see who's here. Stacy, if you wouldn't mind, run those for us. So if you could just indicate where you're located. Stacy, you'll let us know when we've got a reasonable number of participants.
Yeah, kind of what you expect there, the usual Ontario bunches there.
Thank you. A couple from the US, 4 from the US as well. Thank you, folks, for joining in. Appreciate that.
Yeah, let us know in the chat where you're dialing in from in the US.
That'd be great. Thank you. And then next.
Yeah, let's see what people do.
We always kind of like to have a sense of where you fit, what's your occupation within our industry. So a quick one there. Guess we should have put on large building air tightness tester, but.
Well, please put that in the chat then if we've missed
that'd be
it.
great. You've had experience doing it, yes.
There you go. Thanks, Ross.
And our answers, oh, really nice mix. Builder, renovators, thank you. Engineers, architects, energy evaluators, thank you. Very cool. So thank you for that. Was there one more poll?
Yeah, we have one more question related to your
Oh,
whole
yes.
topic today.
Yes, thank you. So this says, have you had any experience with air tightness testing? Have you seen one, been part of one, written a scope of work for one? Just a little sense of where we're fitting here, if this is brand new to you or you have at least some experience with it. And again, if you want to give us some details in the chat, that would be fine too. And we've called it part 3 buildings, large buildings. You heard Enbridge talk about their program, 25,000 square feet and up, but you might be smaller than that and still call it large building. We're typically, for those in the US, commercial buildings for us is part 3. So low rise buildings are part 9, residential. All other buildings are called part 3. So pretty even split. Good to see that there's been some experience. We may be preaching to the converted about half. So that's fine. Thank you for that. Appreciate it. So we did that one. I should have had that up. So let me just take 10 minutes or so and give you a little bit of the what, why, and how of large building air tightness. This is going to be review for lots of you, but I just want to highlight a couple of quick things. And again, I'll say, talking part 3 buildings, and this is a method of calculating or measuring air leakage in and out of part 3 buildings under controlled conditions, right? This is an exaggerated controlled conditions, not the way the building leaks on any given day, but it gives us a measure, relative measure, comparative measure of large buildings. And it's just like testing we've done for years in part 9 buildings. You'll see there at the bottom left, 3 blower doors instead of 1 as an example. In order, you need that capacity, that large capacity to get there. So that's what we're talking about, is characterizing the leakage in and out of buildings. And when we talk about this, it could be buildings like multifamily buildings, whole building air leakage testing. There are also, in these kinds of buildings, individual tests that can be done on suites to measure compartmentalization. And some programs like LEED require that for smoke and fume control. So there's an example of types of buildings. And then you can start to imagine more commercial-based buildings, where the center building there is one of the projects that is going to be highlighted, the Mohawk College building, also a building at Fanshawe. So it could be new or retrofit, publicly funded buildings that require air tightness testing for quality control or HVAC sizing. So we see that. And then just generally commercial, industrial projects that we've been working on. And maybe it's the airtight owner-occupied buildings that recognize there's a value from reducing HVAC size, improving comfort, or saving on energy costs. So these are the nature of the types of buildings that we're speaking of, and different motivations perhaps for each of those. So a little thought. And why air tightness test? And I'm using a quote from Lauren Ricketts from RDH Engineering out in BC. Air leakage into and out of buildings affects building durability. And I want to make it really clear. In 1990, in National Building Code of Canada, there was new segments added, new sections of the code added, both residentially in the residential section, part 9 and part 3, that called for air barriers in buildings. And the rationale was durability. The fundamental reason you want buildings to be airtight in northern climates, specifically, southern climates to some extent as well, is to ensure that there's not leakage of warm, moist air into insulated or cold cavities, no interstitial condensation potential. Occupant thermal comfort, acoustical comfort, and indoor air quality, energy consumption, obviously are all there, but the original rationale for air tightness in buildings in Canadian codes was for the durability aspect. I think that's a pretty interesting piece to keep in mind. And I'd like to go through a little study because I was involved in it, intermodal engineering back in 2003 and 2006, worked specifically with Tridel, sponsored by CMHC, Canada Mortgage and Housing, and did testing, characterization of testing. And they actually found that the suites were tighter than expected. Of course, that's a good thing. It was primarily the type of construction, podium of, concrete construction for the most part, demising walls made out of concrete. It's not true necessarily in wood frame construction, but in general, suites were tighter. Exhaust appliances that were in building didn't move the amount of air they were designed, and yet the buildings would still, in the suites, would undergo significant variations in pressures, plus or minus 75 pascals, based on the operation of exhaust appliances, wind, temperature differences, stack effect, and so on. And really critical, as much as 40% of makeup air to hallways never got to the suites and was wasted. So lots and lots of interesting learnings out of this that we wanted to talk about, and air quality in suites and hallways. So this prompted an interest in specifically in compartmentalization to help control airflow in buildings. There's been subsequent studies done. I haven't been involved in this one. That's why I wanted to show it. There's been subsequent studies done by RDH and others that essentially confirmed these results and went further to show the value of compartmentalization. And I'll go back to that idea of, the motivation. I said it was primarily durability, but indeed, energy consumption is a big deal. Study again, RDH, 16% of office and 24% of multi-residential building energy use is attributed to air leakage. Obviously, a big number that we have responsibility for. Tough to do it after a building's built. Really important that we get it done at least at time of new, and even in retrofit of buildings. So energy consumption is there. I mentioned before durability. This was really about the moisture movement and understanding that air leakage causes 90 times more moisture than vapor diffusion through walls or building enclosures. So that was the primary reason initially for air tightness. And then understanding occupant thermal and acoustical control, just understanding the wind pressures in buildings, the stack effect and mechanical pressures, and what that means for clients' air essentially willy-nilly into the building. I'm mindful of a project that I worked on that the occupant of the 6th-floor suite was subject to cigarette smoke that we ultimately traced to somebody on the opposite side of the building on the 3rd floor. I mean, how did the smoke get from floor 3 west side to floor 6 east side? And it was a combination of stack effect, wind effect, and we were able to track it ultimately. And the answer was air sealing in an older building of those suites. So we can have those kinds of concerns. And I'll get to that idea of indoor air quality, the controlling the pollutants and the pollutant pathways and empowering pressure barriers. The tighter the building, the less air you need to pressurize or maintain pressures within sections of the building can be very vital in buildings that might have 2 different indoor air quality regimes. You might have a welding shop out the back and an office out front. The tighter you make the building, the easier it is to pressurize the offices with respect to the back shop, as an example. So it could be useful in indoor air quality. And I just wanted to remind you the stack effect. It's an interesting one in housing, single family residential, but it's even more important, of course, in large buildings. The higher the building, the larger the stack effect. The colder it is outside, the larger the stack effect. And on a design day in climate zone 5, like Ontario, and my apologies for being Ontario-centric, but you get the idea, 4 to 5 Pascal of pressure per story. Go to Edmonton, it's more like 6 Pascal. You think about a 30-story building, cold winter's day in Edmonton, a 30-story building times 6 Pascal. Boy, that's 180 Pascal pressure from top to bottom of the building difference. And you can imagine if there's air leakage, the amount of air that would move in and out of that building based on stack pressures alone. It also tells you big difference in air movement between summer and winter. And you would like to minimize the difference between summer and winter. And the best way to do that is, in fact, to create airtight enclosures and even within the building, compartmentalization within the building. And so that's kind of the why, and you'll have an appreciation for that. Let's talk, the reference to codes, air barriers. I'm going to mention again, this phrase first showed up in 1990 version of the Ontario Building Code. This is showing the current version, 2012, 2017. And it says an air barrier system shall be installed to provide principal resistance to air leakage, unless you can show that air leakage isn't going to damage the building. But generally speaking, that means air leakage and moist, any building that's conditioned, there's going to be warm, moist air chances, warm, moist air getting into the building envelope. The Part 5 of the National Building Code, just to show we go across country, this very similar language, right? Assemblies shall be such that they control air leakage or permit venting to provide acceptable conditions for the building occupants, maintain appropriate conditions for intended use, minimize, look at C, minimize the accumulation of condensation within that building component, and shall be designed, last statement, shall be designed and constructed to provide that resistance to air leakage to meet those requirements. shall be designed and constructed. So the kinds of phrases. And then we see it in ASHRAE 90.1, similar statements. And it also outlines in 90.1 prescriptive requirements of what is to be sealed. And notice the continuous air barrier. What does continuous mean exactly? Is it perfect? It's never perfect, but designed to provide continuous air barriers within that assembly. So codes and standards do reference this, the interpretation of that, or at least the limits of that. Exactly what do we mean by continuous? How much air does that actually mean? And resistant to both positive and negative pressures. Lots and lots of understanding of what's happening. Codes have good understanding of what's happening. And then when we look at those standards, air tightness testing standards, you will see that there's 3 different levels. There's material standards. Material standards say if you want to know drywall or how airtight OSB is, how tight, say, a water-resistant barrier is. There's the metrics, both in imperial and in metric. 0.02 liters per second of leakage flow measurement per meter squared of material at a pressure of 75 pascals. So you take a sheet good, you'll see there, you would subject it to a pressure of 75 pascal, and you would take the amount of leakage per meter squared. Now, that's not how tight a building's going to be. That's just the material itself. That's a test standard. Then there's an assembly standard, ASTM 2357 or E1677, that says, hey, ship me a wall, 8 foot by 8 foot wall. Put in defined penetrations, windows, doors, so on and so on. And they run it through again at 75 pascal. They run an air leakage test. They'll often do a water test at that same time, but that's an assembly test. And there are some codes and standards, some programs that reference the assembly test. Most codes and standards simply talk about the materials. They don't talk about the assembly. Notice that it's basically 10 times magnitude, right? You expect the assembly to leak more than you would expect an individual material to leak. And then lastly, a whole building standard. And this is kind of what we're talking about today. And we're showing, say, for example, the Toronto Green Standard. Because in code right now, in code, National Building Code, Ontario Building Code, US Code, there is no specific requirement for air tightness. Again, we're showing a CFM, or it could be a liters per second, in this case, CFM per square foot, or it could be liters per second per meter squared of building surface area. This is a little different from residential. Typically in residential, we're using air changes per hour, a volumetric measure. Here we're using a surface area metric. And Kyle and Mike, and I think and others would say, that's probably more appropriate in commercial buildings, more complicated buildings. The volume of the building is perhaps from a air sealing perspective less important than the surface areas. So it's always done as a surface area calculation. That's 75 pascal. Residentially, typically we're using 50 pascal, 75 pascal in commercial, I guess, because higher pressures typically subject to, because of the perhaps more stack effect, more wind effect, and partly because that's what the materials are tested to. But notice that this order of magnitude difference between what you might expect out of a material versus the assembly of the materials versus the whole building. And the standards do point out that, for example, that 0.02 liters per second per meter squared is basically what drywall is. So most codes and standards, ASHRAE 90.1, will deem drywall as being acceptable, OSB being acceptable, so on and so on. So they will list prescriptively wood, for example, is inherently an air barrier, or concrete is inherently an air barrier that could be expected to meet that material standard. So useful to know that you don't necessarily have to test materials. They may just be listed in the standard that says these products are deemed to meet. And there are industry associations that are helping with this. The ABA, Air Barrier Association of America, great training. I would encourage you to go to their website. They have training programs both for testing and air sealing premises. And then there's the National Air Barrier Association, which is more typically material manufacturers, suppliers to the industry. So there are industry associations that help with this. And in terms of air tightness testing, and this is where I'm going to turn it over to Kyle. Kyle, I think you're ready. I'll stop sharing. And Kyle's going to talk about the different types of tests that can be done in buildings and describe that to you. Kyle, are you ready to go?
Yep, I'm ready to go here. Just Bear with me. Okay, yeah, so thanks for that, Gord.
Are you
So
sharing
Gord-
it? You're not sharing it, buddy.
Oh, am I not sharing? It's always that extra click, I forget.
Yes. You got your screen.
There we go. Okay.
That'll do.
So thanks for that, Gord. So yeah, Gord's kind of delved into the bit of the building science about air barriers and overall air tightness testing of large buildings. I'll get a little more into the types of testing when we're talking about large building air tightness testing. So you can test a whole building as a single zone, very similar to how we've been doing it for single family homes. Or you might break the building into subsections, do more of a guarded testing, and then all the way down to your suite testing or your compartmentalization testing. So here we've got a little diagram of compartmentalization testing. Obviously, popular in the multi-family buildings in particular, because that's one of the few buildings you can have where smoking is permitted, other than a private house. So that's why there's a lot of focus on making sure we eliminate any unit-to-unit air leakage, and is why LEED requires on all their projects every suite meet a certain minimum threshold of air tightness testing, both to the outside but also suite to suite. So to compartmentalize dwelling units, as you might imagine, you have to seal penetrations at both the exterior and common walls, ceilings, and floors. You need to seal penetrations to corridors and vertical chases, weather strip exterior doors, operable windows, as you would typically would. And then weather stripping doors leading to common hallways. This isn't always done, at least not with full door sweeps, but it's something it's a bit key because it's not actually something we catch in our compartmentalization testing. We're setting up our blower door fan in the doorway. So that's why usually there's more of a prescriptive requirement for weather stripping that door leading to the common hallway. An alternative is that you test to make sure that the corridor is pressurized more positively than any of the dwelling units. So that's sort of an alternative compliance you can do. But we're seeing more and more of a shift towards making sure that full weather stripping on those suite doors is done. And then we come in and do the suite testing, set up the blower door fan in the suite door, and then here's a list of all the various compartmentalization targets. It's usually an NLR metric you're trying to hit. 0.3 seems to be the industry standard for most programs, and then there's some more aggressive targets that LEED has brought forth, and ASHRAE as well. And so advantages with compartmentalization, of course, we've talked about environmental tobacco smoke control, also just plain for fire code. It's advantageous to limit fire spread. Noise, the more you can mitigate air leakage, sound travels through air leakage, so that'll help with controlling your noise in the apartments. Odors, whether it's cooking or perfumes. Energy savings, of course, it's not as a direct measurement as, say, like a guarded test or a whole building test, but it's still a pretty good proxy to get a sense of how tight your unit is, and it's a relatively easy test compared to testing the whole building or a guarded test on a suite level. And then, of course, comfort goes with all of those. So beyond compartmentalization, there's the guarded testing approach, and that can be helpful. So that's where you're testing subsections of a building, basically trying to eliminate pressure differences between two zones so that your test zone, you're not measuring leakage to the adjacent zone of the building, but you're trying to focus your measurements on leakage to the outside. So you're basically setting up a fan in the test zone. You're setting up a fan in the any adjacent zones to create a neutral pressure plane there. And you can do this either on a guarded floor test level, or you can do guarded suite testing. For instance, if you just want to catch how much leakage to the exterior is happening at a suite. But as you can imagine, that kind of test does take quite a number of fans, depending on the configuration of the apartment. And then moving beyond guarded, we've got, of course, our whole building air tightness testing, where we're pressurizing or depressurizing the whole building to not just 50 pascals, but we're moving up to 75 pascals to counteract the stack effect and the wind that sort of biases our baseline pressures. Typically, don't want to go too much beyond 75. It gets really tricky to come up with sufficient fan capacity, and then you start to run into issues around damage to the building, for instance, or it becomes a bit of a safety concern. So you'd typically be distributing blower door systems throughout the building, multiple systems. Each system might have 3 fans, 2 or 3 fans on it, because you want to create a uniform pressure distribution throughout the building. And the software for this is pretty robust. You can actually hook up, I believe, up to 32 fans in total. So there's quite a bit of capacity. It's just a matter of how many fans you've got and how many people you've got to run them. It's simpler in a lot of ways versus guarded testing, as you can imagine, because you're just doing one test rather than, say, guarded floor test. You'd have to do several to capture the average leakage of a building. But the cons are, you might have to deal with greater stack pressures, especially in the wintertime on a tall building. There might be lots of HVAC penetrations you've got to seal depending on the test configuration you're doing. And then identifying leaks if the test fails is going to be fairly time consuming on a large whole building scale of test. So testing standards, there are a number of them. The ISO is more of an international one. If you're working on a passive house project, you'd probably be using that standard. ASTM is pretty commonplace in North America. Same with CGSB, we use a lot on the Part 9 residential side. And then Air Barrier Association of America and U.S. Army Corps of Engineers have had testing standards out for quite some time. And in fact, I believe their standards kind of helped formalize the more recent standard, the relatively new ASTM E3158. Seems to be becoming the industry standard for testing of large buildings, at least in North America. And here's a list of various codes and standards that have test targets for whole building air leakage. So starting with Energy Star and LEED, it's not a requirement, but it's encouraged to take credit for in like the energy model. IECC and ASHRAE 90.1 both have test targets. And then there's the International Green Conservation Code with a more of an aggressive target to hit. And then, of course, you've got VIAS and Passive House that are sort of leading the industry as far as targets. Passive House doesn't, I believe they don't have an NLR standard like the others. They've still got, they're using the ACH, air changes per hour metric, because it was originally derived for houses. But as far as I know, they don't have any sort of NLR for the Passive House International program. Okay, and then so that leads me into the National Energy Code for Buildings. So there's been some changes with the latest edition, 2020. And so for the first time, the NECB has specified an air tightness test target to quality check the performance of your air barrier. And so this energy code is being harmonized across all the provinces and territories in Canada. I think Ontario is looking at having NECB come into effect in the spring of next year, I believe. And other provinces are following suit as well. So what the NECB has is very much going to be what we can expect to be building to shortly. So the test type that it references is that new ASTM E3158 that's particular for large buildings. And the test configuration is the building envelope configuration. So the idea would be to exclude, or you're allowed to exclude the HVAC openings for the test. And you'd be doing both a positive and a negative pressure test and averaging the results. So 1.5 is fairly aggressive when you consider some of the past data sets we've had on test results for existing buildings, but maybe not that unreasonable for new buildings. And given the fact that it's a building envelope test, not an as operated test, so that does give you the permission to seal up a lot of the HVAC components as well.
And Kyle, you mentioned the data set. When you think about it, there's literally millions of houses that have been tested in Canada and US. When you think about all the US Energy Star houses and so on and their codes, there's a relatively small data set, right? Less than a few hundred buildings. And as you mentioned, some of them were existing buildings. So I'm going to say it's one of the reasons Enbridge is sponsoring and has these incentive programs is to kind of build the database of where are we at before it becomes code. You really would like to know where your buildings are at now. So that's one of the reasons for Enbridge incentive. One of the reasons for the session today is let's find some buildings. Let's build the data set to see how close we are to that 1.5.
Yeah, that's a good point. And I know some of the other jurisdictions that have mandated this, it's been more of a goal to hit the target, but if you don't, it's not like they're just going to shut down the project. There's some steps of sort of lessons learned. You might have to do a few extra steps if you fail, but it really, they're just trying to build the data set for new construction at this point in time. And I'll get to that a bit with I think that's sort of the way the TGS is working it as well. Also in the NECB, there's some guidance on energy modeling of air tightness testing, which wasn't explicitly outlined until recently. So that can be really helpful for projects that are going to try and comply using the performance path, or if they're looking at elevating their performance through one of the energy performance tiers, which will likely be a sort of a voluntary compliance approach. Some jurisdictions might choose to adopt a higher performance tier, or there may be some incentives in place. And then you can come up with some analysis that look sort of like this. This is just an example of an archetype building that RDH, I believe, prepared for like a 6-story MERB out west somewhere. And you can kind of get a sense of where your energy goes depending on the air tightness of your building. So not only space heating energy, but the load of your HVAC systems can be significantly impacted with air tightness levels. And then tying into that more locally, we've got the Toronto Green Standard that is mandating whole building air leakage testing, at least for Tier 2. So Tier 2 and above does require that, and there's various incentives in place to try and get projects to adopt the Tier 2 or higher levels. So they're currently at a 2.0 liters per second. So it's a little higher than what national is. But again, I think the goal right now for a lot of these programs is just to establish a bit of a data set. And then just some other examples of air tightness test requirements around the continent, many jurisdictions in the US, and there's probably more beyond this. These are just some examples. And then a list of countries that we see air tightness testing in place. Okay, so now testing experience, I'll bring it over to Michael Gillizan. Mike, I'll send this over to you, so I'll stop sharing my screen.
I think you were going to run the slides for me.
That's right. Yeah, you want me to run the slides for you, Mike?
Yes, please. Perfect.
Okay.
Thanks, Cal. So the planning, planning and coordination takes up definitely the majority of the time that our team collectively spends on a given project. So first, we're identifying the test objective, whether it's through a program like Enbridge's or the Toronto Green Standard. That'll specify the specifications, and then after that, it's a lot of meetings, coordination internally and externally. So at the beginning, Kyle, myself, Gord, and the rest of our team will look at a job and come up with an estimate, and then really after that, it's site visits. We're talking with building operators, mechanical contractors, and really it does vary quite a bit from building to building. Whereas in residential Part 9 construction with homes, it's fairly repeatable. With large building, it depends, what type of building it is. So again, it's the majority of our time, and then site access is really critical. And the unique thing with large building testing is we're in the buildings. We're typically doing the testing in the evenings or on weekends. So when there's as few occupants as possible, that just alleviates any obstructions while we're testing. So scheduling, we're looking at the weather. If it's possible, we're definitely trying to avoid tall building testing, whole building testing in the winter. So we'd be looking at definitely going a guarded route for example, a tall condo building in Toronto. We'll be looking at doing a guarded approach. Site conditions vary definitely building to building. Security is critical for depending on the building. We just had a job on Monday. The building has not been occupied yet, but it was quite busy even throughout all hours of the night. So security is key.
The term occupancy can be a very gray area term when you talk to the project owners.
Yeah, and accessibility, definitely we want to have access to the entire building, and site support. So having the key contacts, leading up from planning, and definitely when we're on the job, if something comes up, we need to be able to talk to the building operator, mechanical, electrical support. So yeah, the planning, you can't really spend enough time on. This is critical. It sets up a good test. So thanks, Kyle. And here we have, typically we'll do van rentals, just depending on the nature of the equipment that we'll need to bring. And unloading and loading is really the quickest part, but we have a lot of gear, a lot of equipment that we'll be setting up. And a member of our team, Alan, has came up with a prototype. So we call that Frankie on the right there. Hopefully we can share more about that in the future, but it's just
this is a sneak peek.
Yeah, it's a sneak peek. Yeah, that is, yeah. Yeah, thanks, Kyle. So yeah, building preparation, this is critical. Depending whether we're doing pressurization, depressurization, or both, how you prepare these openings specifically for a building envelope test is critical. So we're looking at, it starts in the planning stage, reading the mechanical drawings, and then when we get to site, prepping the openings. Again, really identifying if we're going to be depressurizing, changes our approach. We have a very wide array of different types of tapes we use just to try and be respectful of finishes. So, taping up for a condo building, for example, to high-rise condo building, we'll have hoist suites that are operable, that, the hoist is still operating. So that's a zone that we'll eliminate. We'll kind of compartmentalize that zone out of the building test. So we'll be sealing up those areas. And yeah, thanks, Kyle. So performing the test, this, in the grand scheme of things, it's doesn't take as long, obviously, as long as the planning goes smoothly. But performing the test it's a lot of fun, when things go smoothly. So we'll typically have a team of 4+ people on site. We're using TechLog4. I saw that Jake's one of the participants from Energy Resource helping us out with the software. And yeah, thanks, Kyle. So challenges, lessons learned. So yeah, like previously mentioned, building security and occupants play a big factor while we're performing the test. We did a few buildings, large buildings that were occupied, had people living in them. So that required a lot of coordination up front with the people living there. HVAC components to seal, under pressurization, depressurization, elevators and guarded testing, that's played a key factor, in having clean results. And just taking larger data sets, because when the elevators are operating, it does fluctuate the pressure considerably within the building. Power, unique situation. We were doing a very large community center with 6 ice pads. There's not a lot of outlets on their own breakers, on their own circuits, in an ice pad. So it was a tremendous amount of extension cords, and just really during our pre-site visits trying to plan that out and looking at options for, portable power, whether it be generators. So yeah, doorways for the blower door. On older buildings, rooftop access doorways can be smaller. So if you looking at the drawings, if you think you can fit 3 fans, you might not always be able. So we had a rooftop doorway where we could fit 2 fans. So looking at rough opening size and hardware. And so yeah, the last point, tall buildings, cold weather, big stack effect. So
It's just because you don't like cold weather, is that it?
that's true. Yeah, we discovered gloves and hats, but no, it was we've had a pretty mild December, but it was a cool night, Monday night.
I think you'd agree too, Mike. There's a considerable amount of jerry rigging of, build a little wall to isolate, say, a mechanical room that otherwise isn't sealed, or as you mentioned, the lift doors. So there is a little bit of rough carpentry, and bits and pieces that are needed. So thank you for that. It's that the pre-planning obviously is so important, but even still, you end up with those odd situations. But thank you for that. And folks need to know that Mike is available if you guys have questions or want to go through this. We too feel, as a company, that we're trying to build capacity. We all want to learn off each other. So if others want to connect and chat about this, what we've learned, and you talked about Frankie, we'd be happy to share our best practices. Kyle, we're running a little short of time. Do you want to just run quickly through a couple of the projects and we'll put it off to Josh?
Sure, real quick, I just had a few slides. Just on the variety of projects we've been working on. So here's an existing office, 4 stories, actually went pretty smooth. You know, it wasn't occupied at the time, wide open floor plan. So that's kind of like one of our better scenarios, really. And the test result was sort of what you might expect for an existing building, not too leaky, but not too tight either. It was an interesting one. It was an existing apartment building. So it just required a ton of planning and coordination with the building manager and the tenants to try and get the conditions within the building to what they're supposed to be for the test. So it's buildings like these that can be a little frustrating because you don't have as much control over the variables as you'd like. So yeah, the existing buildings that are being lived in are a tricky one for sure. And here was an interesting one. It was a sportsplex with 6 ice pads. Real challenge just figuring out how we're gonna, you know, what's actually practical to test here. So we ended up actually separating out the ice rinks from the concession area and really just focusing on how leaky are these rinks themselves. We did some interesting tests with taping adjacent doors and not taping adjacent doors. So we got to compare a bit about that, and we got to see how the old rinks versus the new rinks compared. Sort of as you might expect, the old rinks were a lot leakier. And that was an example where it was really hard to find enough power. That was one of the big challenges. Wide open spaces, and you just needed a lot of fan power for that one. And then here's more recently, we did a 15-story MERB, new, and that went fairly smoothly. It's still a lot of prep work, making sure all the doors are propped open, like the interior doors, making sure and gaining access because there was some funky keypad situations on the suite doors, which we didn't quite expect. So there's, you know, this thing you don't quite anticipate beforehand that you learn on each of these jobs. And then these are just some old classics that our former colleague Rob Johnson, now retired, did. These we're pretty proud of these ones. They tested really great, and there was a good team working on those. So those were sort of one of the top performer examples. Yeah, the Ron Joyce Center and the Sifton Center. But realize I better hand it off to Josh here.
And while you're doing that, I'll just say thanks, Mike and Kyle. I think we could say Rob Johnson is one of the only guys in North America that's actually retired from a job of doing large building air tightness testing. Right? It's so new. There's not too many that have been at it that long. So thank you, and again highlighting, and we're happy to share any results of those buildings. But Josh, this was an aero barrier pilot that you were working on, and you wanted to share some of the challenges, testing protocols, and the results. So take it away.
Absolutely. Thanks, Gord, and good afternoon, everyone. So just to get into it, like why is air tightness important to the development community, right? When we're talking about financial benefits, air tightness can actually be a capital cost reduction. An airtight building typically should require a smaller mechanical system. So you can actually get a better building for less cost. That obviously produces energy and GHG savings, and also in the longer term, your maintenance and replacement capital requirements go down. But looking at it too from a building and residence point of view, you know, we're chasing Teddy in terms of modeling for the Toronto Green Standard or the BC Step Code or any of these high performance development standards. Air tightness has to be a critical part of that going forward. But also, as you know, Gord has already said, you know, reducing stack effect, and there's also comfort things, right? Odor and pest mitigation. I think we can all agree, if we think about it, if we're going to live in a multi-residential building, we want our own suite to be an airtight box on all 6 sides, right? To the outside, to the demising walls, to the corridor, and the ceiling. That is the best case for comfort. So, you know, we just have to set different expectations moving forward. So I'd like to introduce everybody to 18 Treaty Way. This was Canada's first multi-residential airtight building done with aero barrier. Every suite in this building was compartmentalized using aero barrier. For anybody in the Greater Toronto area, this building is actually at the Allen Road 401. You can see it from the highway. It's actually a flat iron building, very, very interesting looking building, and it is black like it's shown there in the picture. So next time you're by that area, take a look at it. So the goal of this study was, to construct this first building in Canada, this first large, tall, multi-residential building using aero barrier, to compartmentalize each suite, looking to achieve an average of 60% reduction in total air leakage, and then collect data as we went through and quantify the performance of this building over the long term. And we have an opportunity to do that because if you can see in the picture there, the building behind it, that's a condo building that was built at the same time with the same techniques, the same envelope, except it did not receive aero barrier. So in the long term, we're going to be able to measure the performance of the apartment, which is the sealed building, versus the condo, which is not sealed, because they were constructed in the same way. So this building, 16 stories, 177 units, actually a very efficient building to start with. This building does have a geothermal system using in-suite heat pumps with backup boilers. So, just to get everybody up to speed on what aero barrier is, right? This is the aerosolized sealing of building envelopes from the inside out. It's essentially a pressurize and spray technology where the building or a floor, or in this case, suites, are pressurized with a blower door, and then the sealant is sprayed in the space under pressure, so it finds all the holes and seals them automatically. Think of it like automatic air sealing. Instead of trying to use conventional construction techniques to try to mitigate every hole, every seam as we construct, aero barrier instead fills the gaps automatically. So it makes it much easier and much more predictable to build airtight buildings. I'm not gonna read everything off this slide, but it is a very green building product. It's UL Green Guard Gold, super low VOCs. It seals holes up to ½ an inch, and in reality, we've actually seen it holes slightly bigger than that. And it's accretive to development returns. And I mean, as we move forward in these high performance building development standards, air tightness is no longer going to be optional. I mean, if we look at passive house, one of the 3 mandatory legs of passive house is air tightness, is because you can't achieve the energy targets of passive house without air tightness. That's just the building science. That can't be argued with. So as we move forward, we're going to have to include air tightness in all buildings. Geo exchange, getting rid of thermal bridges like balconies, that'll only get us so far before air tightness becomes really one of the most important things we have to deal with. So this study was done with a collection of a bunch of partners. As you can see there on the screen, we were really trying to bring the industry together on this building to really understand the best practices and make sure that there was good third-party reviews of the data so that we could all be satisfied as an industry that this building was going to perform. So Footprint did the energy modeling for this building. Here at Nerva Energy, we did the suite leakage data and the aero barrier application. Building Knowledge, they did suite, guarded floor, and the whole building testing. And then we had the University of Toronto reviewing all of the data. And we also had some acoustical testing done by RWDI as well. So I think this graph really goes to, the core of what we're talking about in the building. Basically, there's 2 dots on this graph for every suite in this building. It's the brown dot is the original air tightness, and the blue dot is the sealed air tightness. So this is compartmentalization. This is whole suite air tightness, all 6 surfaces of the suites. So you can see we did not quite get to the 60% improvement, but we did achieve 47% and change improvement on the whether you're looking at it from an ACH point of view or a CFM at 50 PA point of view. Either way, they're very close. So a significant improvement in this building and whole suite air tightness during construction. Okay, so that was a great news story. But then we can take a look at the testing too, and we can see with Building Knowledge that before sealing, after sealing, in terms of guarded floor testing, as well as some suite testing, clear improvement in that as well. So, you know, building knowledge was able to confirm, right? Aero barrier had a significant impact on the whole building air tightness. We did have some issues with the guarded floor air testing. It may not have provided as much clarity as we wanted to of the difference between the interior leakage in the suites and the leakage to the exterior. That going forward is looking more like guarded suite testing might be a better way to approach that. University of Toronto did their analysis. They compared some unsealed suites to some sealed suites before we finished sealing them all. A clear path forward. You know, the unsealed suites, just relying on the drywall as the air barrier, definitely performed worse than the sealed suites with aero barrier. And one interesting conclusion was that there wasn't much of a difference in suite leakage between the floors. And this may not be that unusual. You know, the floors are solid concrete. There is penetrations for the mechanical systems, but they were already fire stopped. So, you know, in this case, right, the inner floor leakage was pretty minimal. So most of the leakage that was fixed was between the exterior and also the interior walls on the floors. So from a whole building perspective, when the final test was done just at the end of construction, this building ended up at 1.31 liters per second at 75, which is obviously much better than the Toronto Green Standard targeting at 2. So very, very happy with this results, especially because air tightness was a late addition to this build. So there was even additional things we could have done earlier in the design, but just based on the standard build, the standard design, the air tightness was greatly, greatly improved. And we can see this in terms of the whole building testing, right? Now, this is not the test.
Oh. Did we lose Josh?
I think we lost Josh.
Uh-oh.
So sorry about that.
Interesting.
Josh, we'll have to log back in. So
What,
Gord,
fair enough. We'll let him back in. Maybe we'll answer a couple of questions while
that's a good idea.
while he's away. Let's try that. So Tommy asked, do all units have to be tested in a building for compartmentalized tests? And the typical answer is, well, Kyle, you might want to interject on this. It depends on the program. LEED doesn't say you have to test all suites. It gives you a randomized number. So it would depend on the program that you're running. Is it 10%? No, 5%. Well, you tell me, Kyle. Do you know offhand?
1 out of every 7 for LEED. Energy Star, I believe it's 10%. So it's something in that order. It'd be pretty rare, you know, in a big condo building to test every unit. Not that you couldn't, but yeah, that's it seems to be the consensus is more of a 10% quality check to kind of get you where you want to be.
Thank you. And then Darius asked, tall buildings and cold temps, that big stack effect, why not test during this time as a worst case situation? And Mike, I think you're going to be able to say just because it's the stack effect just puts an unrealistic pressure or adds to the pressure, and it just makes the results more difficult to interpret. Is that a fair statement?
Yeah, yeah.
Higher bias pressure that you've got to offset then, and you don't want to be depressurizing the building to such a degree, because then, well, a lot of fan capacity. There's safety issues, of course. But yeah.
Josh, looks like you're back.
Yeah, unexpected power outage here. Sorry, guys, but we are back. So I'll just pick up from where I left off there. So when we look at the these values here that you see represented on this screen are the infiltration numbers that are used in energy modeling, like EQuest and IES. So we can clearly see here what the Toronto Green Standard default is at 0.25 liters per second meter squared at 5 PA. This building achieved 0.2. Passive house would be modeled at 0.06. Now, one key message about this slide, though, is that it's always been suspected that buildings generally are probably getting credit under the Toronto Green Standard for more air tightness than they're actually delivering on average. And this is part of the reason that the TGS is now requiring testing, although not compliance yet, just testing for data. because we see where the RDH and RWDI values came in based on other studies that have been done by the industry. So, you know, we've got to do better here. We're probably not achieving that 0.25 in most buildings. But that's going to become more and more important, because by the time the Toronto Green Standard rolls around in 2028 and we're only doing passive house level construction, you're going to have to be down around that 0.06 from a modeling perspective, and then have to verify that you actually achieve that at the end of the project. Otherwise, your building is not going to be compliant.
So Josh, I'm just going to stick on that just for a moment. Go back one. Just stick on that for a moment and just highlight again that you're doing the air tightness test at 75 Pascal, but the energy modeling is trying to take that, or at least assume an air leakage at 5 Pascal. So one's an air tightness test standard, the other is a modeling standard for how much air leakage there's likely to be across a wall, across the building at a pressure of 5 Pascal. And somebody would say, well, how do I translate the two? There is a formula that would help you if you know what's called the N number, the slope of the line, that you can translate or extrapolate your results at 75 and down to 5, but it's less and less accurate. And I'll highlight again, as Josh said, we actually think that the standard at 5 pascals is probably lower than what's actually happening on a building. Certainly in Canada, cold weather, buildings are seeing more than 5 Pascal pressure on average over the winter, where the energy use is the biggest. So work has to be done on that. Don't sweat it too much, but this is one of the reasons to build this capacity, is start getting a database of where numbers are at. So thanks, Josh, for allowing me to pipe in there. But so continue on.
Absolutely, absolutely. So in terms of the specific energy modeling for this building, you can see here the infiltration is represented by that light blue bar there, and you can see it shrinking. The item at the bottom, geothermal, is the baseline energy model for this building, and then with increasing air tightness as you go up, you can see that the infiltration amount of the energy load just starts to disappear and almost goes away. Now, G3 is closer to passive house levels of air tightness, but based on the numbers that were run for this modeling, this building practically achieved about the G2 level. So with a conservative reduction in the ventilation system, because the amount of pressurization air you need to provide to a multi-res building is in many ways directly related to the air tightness of that building when you're getting into high performance design. The combination of the infiltration reduction, the improved air tightness, and the reduced ventilation, you're talking almost a 20% reduction in the TEDI, or the thermal energy demand of the building. So that is very significant. It follows along with passive house principles, and it's where the building industry is going, because we have to go to these high performance, even if we're not going to call them passive house buildings or certify them to that. That's the performance level where the entire industry is moving towards. So just like to say, for this particular building, it was recognized by the Canadian Green Building Council last year, the 2023 Green Building Visionary Award. So we're very, very proud of that. The CAGBC is a great partner, and there's even air tightness standards within LEED, and we hope to see those improved when we move into LEED version 5 sometime in the next year or so. Now, we have one other selection of results to share with everybody. Also did some air tightness testing and some aero barrier application at a Tridel building, certainly a very, very well-known builder. So this site was done at the Well, more specifically because the Well is a series of buildings, Building D. This is a 38-story, 400-suite building that's been built in the last couple of years. The suites are as large as almost 1,300 square feet. And, the reason Tridel wanted to do this pilot, they wanted to understand how airtight their as-built suite construction was, because they weren't taking any special measures in this construction. So they just wanted to see, what are they doing today? What benefit did aero barrier provide? And what are the lessons learned for future projects? So what Nerva provided for this building was, we did the suite ceiling on in Building D on the 27th floor. That was just lined up well with the construction schedule. And as was done for the Collective building, 18 Tready Way, the ceiling was performed in a compartmentalized whole floor fashion. Well, really a whole suite fashion. We're compartmentalizing each suite as an airtight box. There was blower door testing done on additional suites. I certainly don't have time to go through all the results today, but there was also different types of blower door testing done. And this was something we actually learned from the previous project, was trying to understand the impact of, the envelope air tightness versus, what impact are the operable windows having, and the balcony doors, and what impact are the HVAC penetrations having as well. So this goes down the road of, whole building design and really understanding where are your worst leakage points. Are they around the walls? Are they around the windows, the operable windows, or are the HVAC penetrations really causing issues? Certainly can't get into all the results today, but you can see here, this is just looking at the wall. So this is with all tape, or what we call the operable windows, the doors, and the mechanical penetrations, all sealed on these suites on the 27th floor. And you can see the before results, before aero barrier in the orange bars, and you can see the post aero barrier results, or sealed results, with the green bars. And, there certainly was varying starting and ending points, but on average, the whole air tightness of the wall assemblies within these suites, the envelope and the enclosure, improved by over 50% after the aero barrier application. So very, very effective from a cost perspective, from a time perspective, and from a reliability perspective of just being able to get in the building in conjunction with the drywall trades, or around the same time as the drywall is going up, and getting those suites sealed after the first mud and tape has been done, so that they are truly that airtight box, and that this can be then expanded to the whole building to, and when the whole building's done, we get a superior whole building airtightness. So yeah, so we had that over 50% improvement. Things that we found through all the results, the exterior window and door assemblies in this building were quite tight. But the HVAC leakage, the HVAC penetration leakage was an issue, especially under pressurization. So what that means is that, especially in the wintertime with the stack effect, sending pressurized air up the building, we know that the HVAC penetrations from the suite are going to leak quite a bit in this building. And it was a very typical design, high performance design for Toronto today. But I'm going to talk in the next slide, which is my last one, about a few things that we can think about in future designs that maybe avoid some of that HVAC leakage. The 7 suites on a few different floors seem to have high initial leakage. We could not figure out what that was at the time, but there was something about the unit 7 on each floor that was really high leakage. But conservatively, and I mean very conservatively, if this entire building had been sealed, there would have been at least a 10 to 20% heating energy usage reduction and a peak heating demand reduction. Likely, probably even would have been a little more than that. But this goes back to this trade-off between the cost to seal and the cost downsizing, or the savings that you can generate in the mechanical systems that no longer need to be as large anymore, because the whole building load due to air tightness is just reduced. And where we kind of see the industry going here for these large buildings, they're just simply more complicated than obviously a single family home, or even a very low rise building. From a high level side, we strongly believe we need to do more integrated design processes, IDP, switching developments to CCDC 30 contracts rather than more typically CCDC 5. So that is going to be a key driver to power developments into this high performance future, at least until high performance development is the standard and the industry has caught up on all the tools and techniques. The other part is we encourage developers, engineers, and architects to use passive house principles and work backwards from those on all new developments. That doesn't mean you're going to try to achieve passive house level of performance on all developments, but the passive house planning package seems to do a much better job at quantifying the benefits of air tightness and continuous insulation, for example, than maybe some of the energy modeling software like eQuest and IES. So maybe we can work at it from both directions to get a better answer as early as we can in the design process. But then the other part of it is building features. When we're talking about these high-rise MERBs, certainly the aero barrier is a key part of the solution, but we need to look at the operable window and door air tightness. Like, there are CSA standards around that, but those standards have bands of air tightness in ranges. So we need to understand what we're actually getting in the building. We need to consider elevator vestibules so that we can isolate the continuous shafts within the building and the airflow associated with them to a small area rather than down the entire corridors. We need to look at more centralized ERV systems, moving away from in-suite ERVs and trying to get suites that have no mechanical penetrations. And that is absolutely possible today. We're already seeing it in the passive house developments with a centralized ERV, recirculating range hoods and ventless or heat pump dryers. You don't need any mechanical penetrations from a suite to the outside. That gives you a whole bunch of additional air tightness just from the design choice. As well, it makes your envelope a lot simpler as well. So there's all kinds of advantages to that once you understand the whole package.
Josh, thanks very much. Really interesting. I'm sure there'll be some questions. I'm going to have you stop sharing, and Kyle will share again just to get the Q&A slides up. But that gives us an opportunity to go to the Q&A, and I'll try to meter those out if that's okay. So let me just, let's see. Katrina's asking, any comments on air tightness testing on new versus existing buildings and realistic air tightness targets for existing buildings? I'm going to start, and then I'll ask Josh or Kyle or even Mike to comment. That's exactly why we need to start building the database. And that's why I'm so proud of Enbridge for stepping up and saying, let us help you. Let's get a database. Let's do as many buildings as we can, new or existing, to figure out those targets. It's going to be difficult. I'm not sure that we have an existing building enough of a database to say. I think you take the existing building as how much can I improve it by, like worry less about what its number is and worry more about how tight could I make it? You know, is it a 20%, 30% improvement? Kyle, any thoughts from your end? Do we have enough data that help us with that?
Well, that's a good question. As far as I know, RDH has done a lot of work just looking at past data sets and possibly CMHC. So there is some data out there, but I still agree we need more, and probably more to reflect new construction. I think there's been a lot of older existing buildings, but we don't yet have enough on new construction. So,
Josh, your thoughts?
Yeah, well, existing buildings, I agree with you, Gord. It's all about percentage improvement and what's practical within the, in terms of actually implementing with the building. Is it just weather stripping? Is it new windows? Is it other things? Because the existing buildings are typically tenanted, so we got to be cognizant of that. On new builds, all the energy modeling that I've seen for new large buildings. We probably should be targeting near passive house levels of air tightness around that 0.6 ACH at 50 or equivalent. I think there was it was posted before, it was about 0.167 liters per second meter squared. So, because the benefits of after that kind of flatten out, like the curve starts to flatten, but they're pretty good up to that point. So let's just set that, use that, and we kind of have to do that because with these TEDI targets coming of 15 kilowatt hours per meter squared for heating, we're not going to get there without that level of air tightness.
Thank you. And then Ben had a kind of a series of questions. He's asking Josh, was air barrier used as the primary air barrier simply to catch mistakes in the primary air barrier? In other words, did you use it to tighten down, or were windows and doors, panel joints not sealed with sealant or tape and so on? But I just want to put it in perspective. Let's get some terminology. I think we would say the primary air barrier would be whatever your WRB is. If it was, for example, a Tyvek, or was it a roll-on spray applied air barrier, or was it the drywall, or was it the poly? So that material, the 8-foot sheets of stuff or 10-foot sheets of stuff, that'd be the primary barrier. And then typically, you're right, Ben, in many buildings, then you would say, okay, I'm going to caulk the around the windows, back rod and caulk, or I'm going to caulk the top plate and bottom plate. So Josh, is that the way it was done, and then you applied air barrier, or did you say, don't bother caulking anything, we'll apply air barrier and see what happens?
Oh no, air barrier was definitely to catch everything afterwards. It definitely was the second part of it. I mean, whether we're talking about sheets of Tyvek, rolls of poly, or just sealing around, window wall, curtain wall assemblies like that, that still has to be done, right? Aero barrier is kind of attacking the sealing from the inside out, and then you still want those sealants on the outside from the outside in, right? So that we got to catch that on both sides. That's my
And the
opinion
hint,
anyways,
and
Gordon.
the hint, Ben, would be that as Josh mentioned, AeroBear is really good at holes half an inch in diameter, thickness, or width, and smaller. So, what you want to think about is if I can fit a spray nozzle of a caulking gun or a foam gun into the opening, might as well do that. Then you're saving AeroBear from doing that. That said, I know the Passivos folks, for example, spend a lot of time after the fact recaulking, retaping, and we would say, let AeroBarrier do that. So do your rough caulks that you need to do anyway for weatherization, and then let the AeroBarrier. Josh, I think you would agree with that.
Yeah, no, I completely agree with that, Gord. And the other thing is too, like I'm coming from the perspective of suites within a multi-res building. So let's say we do a good job on the envelope wall, but we do a terrible job on the demising walls and the corridor walls, right? Typically we don't, constructors are not used to doing anything really airtight on those assemblies. So and we want really in the end, we want that whole suite to be airtight, which is obviously kind of different than when single family homes are done and we're really just looking at the envelope.
Right. We're getting into the rapid round, so we'll be a little quicker on answers, but Ross is asking, always the big question, what's the rough cost of completing AeroBarrier on a project of this size? Maybe you could help Josh understand how is it priced, or what would they need to give you in order to price it?
It's priced on a per suite level, depending on and that cost varies on suite size. Is it a bachelor, 1, 2, 3 bedrooms? But a good budget for large, tall, multi-res buildings is $3 a square foot.
Thank you. Of conditioned floor area.
Of conditioned floor area. Yeah,
Right.
GFA.
Then Jack's asking more of a NBC, NECB, and Kyle, you might be able to help with this or not. Do we have a schedule for the next tier? Maybe it's Toronto Green Standard that he's speaking of. Do we have any understanding? I will say this. I know my understanding is that NBC, they are going to start with tier 1 of the NECB when Ontario adopts. I know this is sounding Ontario-centric, but when the NECB 2020 is adopted, or National Building Code 2020 is adopted, it will be at tier 1. Does anybody have, maybe somebody else could answer, unless Kyle, when is the next tier of Toronto Green Standard?
It's a very good question. If somebody has a firm answer, please paste it in the comments. I'm not always up to date on when the next rollout of these items are, but I suspect it's gonna be a moving target depending on jurisdictions. I see probably different jurisdictions adopting different tiers or different incentives for different tiers. Yep. So it may not be, what's Ontario going to do, but it may be what's your specific region planning to do type of question.
Yep. And Kyle's
I do have a comment there regarding the Toronto Green Standard. Like what we're kind of seeing in the market today is to get to the current minimum requirements. Builders are kind of doing two things. They're doing geofields. And they're starting to strip the balconies off buildings, those thermal bridges, because thermally broken balconies are very costly. So those two things today will get you mostly compliant with TGS where it stands today. But airtightness is really going to be a key part as we move forward, because otherwise it's the next kind of easiest thing to attack.
Okay, Jack, Kyle's going to answer your other question, typing what software was used. Emily asked, and we have 5 questions in 1 minute. So rapid round, guys, 20 seconds. Emily is asking, could you speak the difference between positive and negative pressure regarding results? Mike, you would have some experience with that.
Yeah, to generalize, under positive pressure, it tends to be a little bit leakier. And it depends on the type of building. If it's a residential building, we ideally will depressurize it. We're sucking dampers shut. So depends on.
And the issue really is dampers that are, spring loaded, gravity dampers that are now pushed open, windows that are now pushed open, if you will, during the positive pressure. And it really comes down to what are you trying to test? As Josh indicated, sometimes you're just trying to test the wall itself and you've got all that stuff taped off. You might not see a big difference. But in general, as Mike said, positive pressure is worth. And then Ben's asking, was building D using hallway pressurization or dedicated supply? Should be a quick answer.
Well, for
Oh,
ventilation.
yeah,
Yeah.
that's for me, yeah.
Oh.
No, that was sweet supply. So,
Thank
you
you.
know,
That's it.
we're not trying to, in aero barrier in MURBs, tall MURBs, it only makes sense to seal each suite as an airtight box. It doesn't really make sense to seal the whole floor. We've actually
Right.
costed it both ways. You get a better result and it's about the same price if you just seal each suite individually.
Almost out of time. Jeff is asking, will tiered energy code allow for encouraged guarded testing? It's already allowed, quite frankly. It will depend a little bit on interpretation moving forward, but guarded testing is already allowed. Liam's asking, are the recirculating ranges and dryers comparable in quality to the existing style? That's perhaps a little tougher to mention. Will they meet the needs of clients? Will they meet the expectations? And that's always a good question. I think ventless dryers probably have a better, from an air quality perspective, not as big a concern. Recirculating range hoods from an indoor air quality perspective are certainly a big concern, and we'd have to show equivalent exhaust capacities.
Well, keep in mind on that. Tridel as a builder has standardized on the heat pump ventless dryers for years now. So
Yeah.
if they're
doing
doing
well.
it, they're one of the leaders. In terms of the recirc range hoods, keep this in mind. To meet code, you still need an exhaust port in the kitchen. So that would typically be in the ceiling or the bulkhead above it. So it's not that you don't have any direct exhaust in the kitchen. The difference is it's tied to a centralized ERV system, not an in-suite ERV system. So that air, there's still no penetration in the suite, but you still have exhaust in the kitchen. That is still required.
And then last question, then we'll go quick. In a high-rise building, when doing guarded floor by floor, would sampling approach be considered acceptable? Kyle, I think you and Mike can answer that.
Yeah, sampling would be the way to go, for sure. Very impractical to do every floor guarded. But the protocols, like TGS's protocol, would allow that.
Yep. So I'll say thank you to Josh, to Kyle, to Mike for presenting. Please, everybody, join me in a round of applause. No, kidding. Thank you very much for this. I will say one last time, we all understand on this call that this is a starting point. This I think Enbridge is brilliant in incentivizing this to get a database. We are open to sharing any of the results of our work and our techniques and so on. So if you want to help us with that, want to engage with Mike or Kyle, please let us know. We want to be inclusive. And then I'll say our next series, in fact, it is a series within a series, starting soon in 2024, will be a 3-part series on the new Ontario, what will be the Ontario Building Code, NBC National Building Code, when it gets adopted. This will still be applicable to others at the various tiers. So we'll look at prescriptive requirements, performance compliance, and then multifamily compliance. And I think we have perhaps one last slide, do we? Maybe it's just a goodbye slide.
Oh yeah, we have, whoops, sorry.
Yes. We would just encourage you to be part of our newsletter, sign up for Building Knowledge newsletter, and new digest is what we call a quarterly newsletter and digest. So thank you all again. And thanks again to Enbridge for helping with that. We'll leave this slide up just as we leave. You will be getting a copy of the presentation, but thanks all for your participation and for the questions. If we didn't get to all the questions, we will answer them after. Good. Kyle, you were going to answer the question to Jack on the what software was used for the modeling.
Oh yes, I can answer that one for sure.
Yeah. Thank you. Thank you all. Sorry, we're a couple minutes late. Thanks again.
Thanks, everybody.
Everyone.